of special factoring rules that show up so often in calculus that it's really important that we have them memorized. So the first, we talk about the difference of squares. And an example of this would be something like x squared minus 16. This is a perfect square, and 16 is also a perfect square. So when we talk about factoring this, we're saying, can we rate this as a multiplication problem, where this is the answer to that polynomial multiplication problem? And the special thing that we've got for the difference of squares is I'm going to write, I know that to get an x squared, I need an x times an x. And to get 16, I need 4 times 4. And when it's the difference of squares, one of these terms gets a negative sign and the other gets a positive sign. Well, what's happening when we multiply that out, if I were to just check my work over here, when I multiply through on the x, so I'll do x times x, and then x times 4, and then come through and distribute my negative 4. So negative 4 times x and negative 4 times positive 4. When we have this difference of squares thing, these middle terms cancel out. That's kind of what's magical about the difference of squares. So in general, when I have something that looks like a squared minus b squared, that should factor as a minus b times a plus b. I'm going to give you a little pro tip, and for some reason, when I write something like x squared minus 16, I bet most, or at least some of you, would have known that this is how it was going to factor. But then our brains do this weird thing. When I write this not in the order you expected, so if I wrote this as 25 minus y squared, suddenly, what a lot of people do is say, ooh, the minus sign is in front of the y squared. I need to somehow factor out a negative sign. My recommendation is don't. This is still in the form of something squared minus something squared. So just keep it in the order that it's in. If this says 25 minus y squared, then I'm looking at a 5 and a 5, a y and a y, one's minus, one's plus. If that really offends your sensibilities, it is totally fine to factor a minus sign out first, but it's extra work and it's extra time. And since our goal here is moving on into calculus, the issue is this isn't the calculus part. This is just the algebra that might be part of a calculus problem. So we want to get a little bit faster and more efficient with the algebra part so that we can concentrate on the calculus part. Okay. Memorize difference of squares. We got another one, which is the sums and difference of cubes. This is another one that you're going to need to memorize. So I'm going to erase this. And then we'll get to the fun factoring. So on the difference of cubes, again, we've got a formula for this. If I had a cubed minus b cubed, this factors, and it starts off in kind of the same way that our difference of squares factor, meaning I'm going to have that a minus b term. Then this next factor is going to look like, if I think about this, if this is going to factor and this multiplication problem has to equal that one, then what times a is going to give me that a cubed? Well, it's a squared. What times b is going to give, what times negative b is going to give me negative b cubed? That's a plus b squared. And then it turns out that the term that goes in the middle is plus a times b. It's a formula. We should get it memorized. Just as a quick example. Oh, and one other thing. That's our formula for the difference of cubes. When we're talking about sums of cubes, there is also a formula for that. And it's really similar. I'm going to start off with a plus b because there's a plus here. And I still need that a squared and the plus b squared, but what goes in the middle has the opposite sign. So that's a negative ab. So if I had something like x cubed plus 27, 27 is 3 cubed. So that's telling me that my b is a 3 and my a is equal to x. So when I plug that into the formula, this turns into x plus 3 and then x squared minus 3x plus 3 squared, which is 9. So when it comes to things being cubed, we have a formula, regardless of whether it's a difference of cubes or the sum. Oops, not sum like S-O-M-E, sum like S-U-M. We have formulas for cubes, whether it's the sum or the difference. When we have things that are squared, it only factors when we have the difference of squares. If I had something that looked like x squared plus 4, there's no way to factor that. Super quickly, go through this one, and I'm going to show you what I would actually do to factor this. And then when we go to the next one, I will show you a couple of different methods. So if I'm looking at this, by the way, this is a trinomial because I've got 3 monomials that are, I've got addition or subtraction of 3 monomials. I don't really care about that vocabulary, but the word trinomial comes up sometimes. Tri meaning 3. I got 3 pieces. When I go to factor this, I'm trying to undo some sort of multiplication problem. I know that when I'm multiplying these 2 pieces together, I have to end up with an x squared. So when I look at this, I'm thinking I need an x here and an x here. Then I know that if I'm doing this multiplication problem, that x is going to get distributed and it's going to get distributed and this number is going to get distributed and it's going to get distributed. But in the end, that 8 had to come from multiplying 2 numbers together. So I'm first just going to think about that 8, and I'm going to list out all the multiplication problems that can give me 8. 8 and 1, 4 and 2. I think that's it. And I'm just going to try them. The other thing that I'm going to look at is I'm going to pay attention to the signs. And the fact that this is positive means whatever we're putting in here have to have the same sign. So if I think about putting in an 8 and a 1, and I super quickly think about distributing, that's going to give me kind of those middle terms I've already made sure that my x squared comes out and then my 8 comes out. But when I look at those middle terms, that would come from doing the x times 1 plus 8 times x. That is not going to give me a -6. Even if these were negative, so that I had -8 times -1, right? I'd have -x plus -8x. I'm not going to get that -6x. So that combination doesn't work. And I move on to look at my next one. And I got that 4 and 2. So I'm looking at a 4x and a 2x. And I'm thinking, okay, well, if I've got a 4x and a 2x, can I build a 6x out of that? I sure can, as long as they're both negative. So option 1 for factoring this is to start off the same way that I did in that previous problem. I want this thing to equal something times something else. Well, if we think about how this multiplication is going to distribute out, this times this is going to have to give me that 2x squared. So I'm thinking, how can I get a 2x squared from a multiplication problem? Well, the only way I'm going to get 2x squared is 2x times x. The next part I'm going to look at is that -12 back there. And I'm going to think, okay, so for the -12, that also has to be a multiplication problem. And I can list out all of the ways that I can multiply together to give me 12. It doesn't take that long to write them down, and writing them down can kind of help you potentially keep track of what numbers you've already tried. So I'm going to write them all down really quick. So 12 and 1, 1 and 12, 6 and 2, 2 and 6, 3 and 4, 4 and 3. And I think I got them all. I think those are all the ways that I can multiply together to be 12. Now here's the real trick. If I look at my original equation, is there any number that I can factor out of all of the terms? I'm going to go with a no. So if there is no number that I can factor out of all of the terms, then that means that when it's factored, there also shouldn't be any number that I could factor out. And right away, I can cross out half the things on this list. So if I were to put in a 12 and a 1, then I would have been able to factor a 2 out. So that's not an option. If I were to put in a 6 and a 2, then I also could have factored a 2 out. So that's not an option. If this were a 2 and a 6, I could factor a 2 out. And if this were a 4 and a 3, I could factor a 2 out. So now I'm left with only 2 that I actually have to check. So I'm going to pop them in and see what we can do. So if I use 1 and 12, and then I think about what those middle terms are when we distribute everything, that's going to give me an x and a 24x. Well, there's no addition or subtraction problem that can take an x and a 24x and give me a -5. So this option doesn't work either. So my last best hope is that this is going to work for us. I'm going to put in a 3 and a 4. And say, okay, well, those middle terms, when I go to multiply them, I'd have a 3x and an 8x. Well, I can use a 3x and an 8x to get a -5x. I just have to make sure that that 8 is negative and the 3 is positive. So I'm going to put a minus in front of the 4 and a plus in front of the 3. Method. And so option 2 for thinking about how to factor is to think about this box method in reverse. And sometimes this is called the X box method. Not because you pull out your gaming console, but because I'm going to draw an X in a box. So for this X box method, the way this works is I'm going to put numbers here and here. And the numbers that I put here and here are going to come directly from whatever it is I'm trying to factor. I'm sure that somewhere along the line, you all have seen the quadratic formula. So if I were to look at this quadratic, we label the coefficient on the x squared term A, the coefficient on the x term B, and the constant that's being added or subtracted at the back as C. So when we do this X box method, what goes up top is I would write A times C, and on the bottom, I would put the B term. So if I'm looking at A times C, I would do 2 times negative 12 and get negative 24. And then my B term here is negative 5. What I'm looking for in these other 2 spots are 2 numbers that multiply to equal negative 24 and add to negative 5. Now with this negative 24 and the negative 5 here, I'm just, again, kind of stuck with this guess and check element, which if it helps you to keep track of what you've already tried, I would just list out the factors. So I'm thinking about factors of negative 24. So what are my factors of negative 24? And I'm not going to worry about the pluses and minuses just yet, but if I think about 24, 24 is 2 times 12. I guess it's 1 times 24. 6 times 4, 3 times 8. I think those are all the factors. So now I'm looking for a pair of these that if I got the plus and minus signs right, I could add together to be negative 5. Yep, and I'm looking at the 3 and the 8. So I can throw a 3 and an 8 in, and in order to get the minus signs right, I'm going to need a negative sign on that 8. Now my next step, after I've figured out what goes in the X, is I fill out the box. To fill out the box, I'm going to start by looking at that A and C term, and I'm going to put the 2x squared here, and I'm going to put the negative 12 here. And then I'm going to take these 2 numbers that we just got, the 3 and the negative 8. I'm going to attach x's to them and fill in these 2 boxes. It doesn't matter what goes where. It'll all work out the same way in the end. So let's say that I decided to put the 3x here and the negative 8x down here. And we haven't actually figured out what the factors are yet. But if you remember from doing the multiplication with the box method, it's the numbers that are out here on the outsides that are going to end up being my factors up top. And the way that we find those is we individually factor each row and each column. So if I look at this first row and I'm looking at the 2x squared and the 3x, I'm thinking about what do they have in common that I could factor out of each of those. And the only thing they have in common is an x. If I look at this second row, negative 8x and negative 12, what do they have in common that I could factor out? And that's going to be negative 4. Then I move to look at the columns. So if I look at this first column, 2x squared and negative 8x, what would they have in common? Well, they definitely both have an x, and they both have a 2. So I could factor out a 2x. And then if I look here, the only thing these two have in common is the 3. And if we just do a quick check in terms of the multiplication, I know that to get each element in the box, it should come from multiplying the edges together. So that negative 8x is negative 4 times 2x, perfect. The negative 12 is negative 4 times 3. 2x squared is x times 2x, and 3x is 3 times x. So now I write my factors up here. 2x plus 3 and x minus 4. So there was a question before about, like, will it always be 3 terms? So it's definitely not always going to be 3 terms when we're not always going to be talking about factoring trinomials. In general, if I see a problem and it's asking me to factor, the very first thing that I'm thinking about is, do the terms have anything in common that I can pull out of all of the terms? So when I'm looking at this and I'm thinking about that 3x to the 4th and the negative 27x squared, they both have at least an x squared in them. And because 3 is a factor of 27, I can pull out 3x squared. Well, if I pull out 3x squared, then thinking about this, 3x squared times what would give me 3x to the 4th? And the answer there is x squared. If I'm pulling out 3x squared from that 27x squared, I'm going to be left with a 9, because 3x squared times negative 9 is going to give me back the negative 27x squared. Now I'm not done, because what I'm left with factors more. This is the difference of perfect squares. So I'm looking at 3x squared, x minus 3, x plus 3. Same kind of starting point here. I'm thinking about, is there something that these two have in common that I can factor out from both terms? And in this case, the only thing that they have in common is that y. And if I factor out a y, then from the y cubed, I'm left with y squared. And from that 36y, I'm left with a 36. And then I do a quick check and I say, hey, does that factor more? And it doesn't, because even though these are both perfect squares, it's a plus. So I can't make those middle terms cancel out. I think I can squeeze one more in on my board before I erase. So let's say that I've got 8x cubed plus 64. You might look at that and immediately say, oh, that is the sum of 2 perfect cubes. But if you don't see that it's the sum of 2 perfect cubes, you might also look at that and say, is there something that I can factor out from both terms? And I can, because 64 is divisible by 8. So I can factor that 8 out. When I pull the 8 out, I'm going to be left with x cubed plus 8. Now at this point, I definitely have the sum of 2 perfect cubes. I'm going to apply that formula. That 8 is 2 cubed. So that means that when I do the formula, I'm going to have the 8 that I started with. My a is equal to x, my b is equal to 2. So I'd have x plus 2, square the x, square the 2, and subtract 2x in the middle. Okay, here, I'm going to be real honest. I don't ever use this method. It's presented in our textbook, and I know some people like it, so I was really trying hard. But I don't ever use this method in real life. So rather than confuse folks with it, I either need someone to help me out right now and tell me what I'm doing wrong, or we're just going to go do this the other way. The thing is, if you do use the Xbox method, the completed guided notes from last year have the problems worked out in the Xbox method. So you'll have that if you want to go back and look at. Okay, so this one's ugly. I'm not going to lie, we got X's and Y's in here. And a whole lot of possible options for how this thing's going to factor, but not nearly as many as it looks like if we just start writing them down. So the first thing I'm going to check, is there anything that all the terms have in common? And there isn't. 2, 7, and 15 aren't going to factor out. So I'm going to jump to thinking about, I need two things to multiply together. Well, these two terms, when they multiply together, have to give me 2x squared. And there actually isn't an option. There's only one way to get that 2x squared. I need a 2x and an x. The place where we have options is on that 15. So the 15y squared term, that's going to come from multiplying these back two pieces together. So I'm going to list out all of my factors of 15. So 15 and 1, 1 and 15, 3 and 5, 5 and 3. I do a quick check. Nothing factored out of the first one, so I can't have anything factor out of this. But all of these are odd, so no matter which one I put in, I wouldn't be able to factor out at 2. And now I'm just going to try them all. So if I think about putting in a 15 and a 1, I'd have a 15x and a 2x. There's no way, sorry, I'm missing y's on this because that was a 15y squared. That would be like a 15y and a 1y and a 1y and a 15y and a 3y and a 5y and a 5y and a 3y. My bad. But $15xy and 2xy, I cannot add or subtract those to go 7. I swap those around and put in a 1 and a 15. Now it's even worse. Now I've got a 30xy and a 1xy. I'm definitely not making a 7. I will put in a 3 and a 5. 2 and 5, that's a 10xy and a 3xy, and I can build a 7 out of that. I'm going to need my 10xy to be positive and my 3xy to be negative. And I'm done. Pausing in case there are questions.
I think the only thing that has me a little stumped is the reasoning, like why you can't use them backwards.
Like why that can't be a 5y here and a 3 here, or the positive negative.
Yeah, why it can't be the 5y and the other one and then the 3y and the 4.
So if I swapped those and I put in a 5y and a 3y here. So if I put in 5 and 3, then when I do my distributions, I'm going to end up with 2 times 3, so that's 6xy and 5xy. But 6 and 5 could give me a 1, or they could give me 11, but they can't give me that 7. So anytime we're doing this factoring, there shouldn't be more than one way to split them up. Only one set of numbers should work. Now, which order you put them in, meaning like you could pick up this entire piece and put it in front, that would be fine. but you can't just switch the numbers up. And what did this have to be? That had to be negative. What factoring by grouping does is that we kind of look at this, and although there are 4 terms, we think about it as a couple of groups. So if I think about this as a group and this as a group, in each one, I'm trying to find a common factor that we can pull out. So if I look at the 2b plus 6 and I'm thinking, hey, what can I pull out of both of those? I can pull out a 2. And when I do, I'd be left with b plus 3. When I come over here and I think about, well, what can I pull out? They both have an a. And then the 3 and 9, I can pull a 3 out of both of those. So if I pull a 3 and an a out, then what I'm left with is b plus 3. So my first step was to group and then to find a common factor that I could pull out of both pieces. And then the last step is I factor my factors. So when I look at this and I think about this entire factored group and this entire factored group, what do both of them have in common? And it's b plus 3. So when I pull out b plus 3, then from this first piece, I'm left with 3a. And from the second piece, I'm left with 2. Now, I have used a whole lot of board space to do this, and it was intentional. For some reason, if you just give yourself the space on these, the factors like fall right out of the board for you. But if you keep scrunching it up so that everything is lined up all the way on your left-hand side, for me, it's harder to visually see how those pieces are coming out. So whenever I'm doing a factor by grouping problem, I actually start by writing the problem more in the middle of my paper, not all the way off to the side, because I want to leave myself the space. Last step, and we don't really have to do it, but visually, this is so spread out, I might take a moment to just kind of collect that as b plus 3 times 3a plus 2. There are more than 3 terms. It is not a trinomial, so I'm going to think about factoring by grouping. I will group those 2 together and group those 2 together, and then look for something they have in common that I can pull out. Well, if I look at this first group, I can pull a 2w out of both of those terms. And when I pull a 2w out of here, I'm left with an x. When I pull a 2w out of here, I'm left with a 5. And really, that's because when I distribute the 2w back in, I would get what we started with. Doing the same thing on the second part, that's 7x plus 35, I can pull a 7 out of both. And I'd be left with x plus 5. Now I look at my 2 factored groups and look for the factor that they have in common. And the factor they have in common is x plus 5. Which leaves me with a 2w for the first part and a 7 for the second term. And again, we can just take that last step to regroup those to say x plus 5 times 2w plus 7.
What if when we group them together, they don't have anything that factors out? Do we just leave it as is?
Yeah.
Okay.
Now, sometimes they're not conveniently already in an order where you can see what factors out. Sometimes you might have to pair the terms differently. Sometimes you might just choose to pair the terms differently. Because factoring by grouping also works with trinomials. You just have to separate the middle term for yourself. Here's what I mean. And this is just yet another method for factoring. You don't need to take notes on this. I'm not going to ask you to do this. It's just another thing in case this is maybe the thing that clicks with you the most. We had a math specialist who used to work here. She's moved on with her life. But Emily used to factor absolutely everything by grouping because it just made more sense in her head. So if I look at this trinomial, I'm going to channel my inner Emily and say that 7xy, I'm going to break it up into two pieces. And I need those two pieces to have something in common with the 2x squared and something in common with the 15y squared. So I'm going to break that 7xy up into a 2xy plus a 5xy. Well, when you do that, and then we think about this as two groups. From the first group, I can factor out a 2x, right? I think I can factor out a 2x from both of those and get an x plus y. I don't know if this is going to work. I'm just trying something because it sounded like fun. And from this second group, it looks like I can factor out a 5y and get an x minus 3. Nope. I can get an x minus 3y. And clearly, I suck at trying to use this method too. I was really hoping that this was like magically going to solve the world's problems. And it didn't on my first try, but it will on my second try. You ready? So that sounded like a good way to split it up. But when I did it, I didn't get two terms that matched. So I didn't get something that magically worked to factor out for us. But what I just realized is that if these two terms are both positive, and over here I have a positive term and a negative term, I'm never going to get these pieces to match because I'm always going to have a plus and a minus. So if I break that 7xy apart, I'm going to have to find a way to break it apart with a positive number and a negative number. So I think I chose a terrible first example to try to do this on. Clearly, what I hope I've demonstrated today is there are lots of different ways to factor, and there's probably at least one way that's going to make more sense to you. And when you watch people do the other ways, just go la, 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 and ignore it. Because if you've got something that's working for you, own that method of factoring. Okay, do y'all want to watch me fight through this because it'll be amusing? Okay, let's go for it. So I've already established that in order for this to work, this thing's going to have to be negative so that I'm like, can also factor out the negative. So, what if I pulled out like a -3 and then this would have to be a +10? And then over here, let's just give it a shot. Little bit of trial and error here. But over there, I could then pull out a negative 3y, and I'd have x plus 5y. Yeah, and then over here, I could pull out a 2x, and I would have x plus 5y. And now it works. Also, I got to give a shout out because Melanie helped me out in the chat, even though I hadn't seen it yet. But thank you, Melanie, for my -3 and 10. So now I can pull out from the entire thing that x plus 5y. And then I'd be left with 2x minus 3y. Is that what we got before? It is what we got before. Sweet.